Okay, it is time to look at our partition procedure. So here's partition. We pass in an array, we pass in a leftmost index and a rightmost index. So what partition does is it takes the entire array every single time, but it's going to zoom in on the subarray here. So from left index up to but not including, so this is not including, exclusive. So not including the rightmost index. And it's going to do a partition on just the elements inside that batch. So not the entire array, just the elements inside that batch. Okay, so we're going to pick out our pivot value, and it's always going to be the leftmost value in the array, the leftmost of our current subarray actually, not in the entire array. We'll set I equal to left index plus 1, and we'll initialize j to left index plus 1, just like we said on the previous slide. And j is going to go from that value up to but not including right index. And every time we look at a new value in the array, so we're always going to look at this next unpartitioned value, so that's the next unpartitioned. We always increment j. That's why j is in a for loop, and why we increment I somewhere else, so not as part of the for loop structure. Alright, well each time we're going to compare the current element, the current unpartitioned, with the pivot. And again, we only have to do something. We only have to do a swap if it belongs in the smaller than partition. If it belongs in the greater than partition, we just increment j, which is done on the for loop line. So we do our swap, and then we increment I, and then after the loop is done, we're going to swap the pivot value, which is at the left index, with 1 to the left of I. And in our partition procedure, we're actually going to return the index of the pivot. So I minus 1 is the index of the pivot after the swap. And we're going to use that in the rest of the function. Alright, well what's the asymptotic running time of this function? It's just going to be linear, because we're looping linearly over this part of this subarray. So it's big O of n, where n is just right index minus left index. Another key to this is that it's going to do in place, so it's not going to require any extra memory allocations. And in fact, a lot of the time, all we're doing is examining an element and then incrementing right index. So it's doing very little work, which is good. Alright, so these squigglies should have been deleted, sorry. Let's look at Quicksort now. So this is our actual implementation of Quicksort, not the bad Quicksort. We're going to pass in array, left index, and right index. And what should our base case be? So what signifies that we don't need to do any more work? Well, our base case is going to be whenever the current sub-array that we're looking at, so denoted by the left index and right index, whenever that sub-array is empty. And it's going to be empty whenever left index plus 1 is greater than or equal to right index. So if I draw an array here, and my left index is here, and my right index is here, well, left index plus 1 is going to put me at the same spot as my right index, and there are no values in that subarray to partition. Alright, well, for the version of Quicksort we're going to look at today, we're just going to always assume that our pivot is going to be the leftmost element, so I'm just going to put a generic function in here called move pivot to left. You can imagine it does it in any way possible. Maybe it does a deep analysis of the array. Maybe it does it randomly, which we'll also look at, but it's going to move an element to the leftmost spot. Maybe it's a no operation, so it's just going to take the array as is. And then we partition. So our partition procedure, like we saw, takes in left index and right index, and it gives us back the pivot index. Okay, so now that we've partitioned, we have to call Quicksort on the less than partition and Quicksort on the greater than partition. So what I want you to think about are, what are the parameters that I send, the arguments I send to the two recursive calls? So what is left index and right index for the other two partitions, the less than partition and the greater than partition? Okay, well, the less than partition, let me draw the full array for you here. Let's say that this is the array portion that we're currently looking at. Sorry. So that would mean my left index is here. That's left index, and my right index is here. Right index is always going to be 1 beyond the end of the current RIGST, of the current array that we're looking at. Well, after I do some partitioning, I'm going to end up with a pivot. Let's say the pivot ends up here. And what I'm asking is sort of, how do I send this to the left recursive call and this to the right recursive call? Well, the left recursive call, I'm gonna want all of these elements, which is from the left index up to the pivot index, because the partition procedure assumes that we are exclusive to the upper bound, so I'm going to give it the upper bound of the pivot. This will make more sense when I go back to partition, and I'll have both of them on the same slide in a few slides for now, or that may be in the next set of slides actually, sorry. Okay, so left index up to but not including pivot index, and then for the right one it's pivot index plus 1 up to but not including the rightmost index.